Okay, welcome to this week's hottest seminar. Today we have Bastiaan Cnossen from the University of Regensburg. He'll tell us about synthetic category theory in CaTT. Please go ahead.
Yeah, thank you for the introduction and thanks for the opportunity to speak in the seminar. Um, so I'm going to report on a joint project with Ivan Kobe, who is also in the audience of the Zoom meeting, which is about synthetic category in CAD. And the approach we are taking is quite different from the usual approaches to synthetic category theory. So I would like to start the talk. Maybe the first third of the talk will be about um, some background motivation for synthetic category theory and setting up the way that I would like to think about this. And this motivates also the use of this type theory that is in the title, this type theory CaTT, which I am expecting is unfamiliar to many people in the audience. So I will spend maybe the second third of the talk explaining what this type theory is about. And then in the last third, I will sort of lay the foundation for like describing synthetic category theory in this type theory. Okay, so first, let me start by motivating why I'm interested in synthetic category theory. So, in recent years, it's becoming clearer and clearer that a lot of homotopy theory, in some sense, is captured by the theory of infinity one categories. I put it in square quotes that it's sort of equal to the theory, but um, what I mean by this is that it's a natural language to formulate a lot of constructions in homotopy theory in. And originally, this structure of infinity one categories, it was very, people studied specific models, they worked with quasi-categories and so on. And in recent years, there's a trend that researchers um, start to write things on a higher level where you are just directly using the language of infinity one categories, and the arguments, they don't really depend on which precise model you choose. Um, and the question that we are addressing in a joint project with Szynski, Nguyen, and Walde is, can we write down some basic axioms and build up a theory of infinity one categories that sort of, captures this model agnostic approach. And then maybe, with the goal of eventually finding some type theory um, to formulate all of this in. And I mean, the reason why this is interesting is that, all these usual structures that we encounter from stable homotopy theory and higher algebra and the theory of infinity one topoi, they they just inherently only rely on they are inherently about the theory of infinity one categories and not about specific choices of models. Yeah, so um this leads to the question, can we find a type theory that captures this model agnostic language? So in other words, is there a type theory for infinity one categories? Um, and of course, I mean, we are not the first that asked this question. So people have been studying this already for a while. And in the literature, there are two main approaches to studying synthetic category theory, and both are based on Martin-Löf type theory. So the first approach, I think it's commonly called directed type theory. And some references are Licata Harper, Neutz, North, and Altenkirch Neumann. And the idea is to take usual Martin-Löf type theory, except that the identity types that are usually symmetric in nature, so an equality from x to y can be inverted to give an equality from y to x. We now replace it by Hom types that are inherently asymmetric. So we have a Hom type from x to y, which we can compose the morphisms and we can have still identities, but we no longer can invert morphisms. And this leads to some intricacies regarding variance and so on, and all these different type theories, they sort of treat this notion of variance in one way or another. And then there's a second approach, which is also based on Martin-Löf type theory, And it just keeps the equality types of Martin-Löf type theory directly the same, but it adds additional layers to the type theory that allowed us to talk about, morphisms in a type, maybe commutative diagrams, and then we can select certain types that behave like categories. So those are called the Siegel and the Resk types, in which there is a notion of composition, which is sort of unique up to homotopy. And I think I like both of these approaches, and I think especially this simplicial type theory, uh, it has seen a lot of progress recently. So I should mention that type theory itself was set up by Riehl and Schulman, and then further work was done recently by Buchholz, Weinberger, and then later by Gratzer, Weinberger, Buchholz. Um, and yeah, but the approach that Ivan and are taking is quite different. We are not building on Martin-Löf type theory. And yeah, even though I like Martin-Löf type theory, it doesn't quite match with the way I am using higher category theory in practice. So one thing that is notably different is that in Martin-Löf type theory, there's a lot of emphasis on judgmental equalities. So for example, if you have morphisms of types, then you can compose them, and then composition is like strictly associative. And this question of whether two maps of infinity groupoids should be strictly equal is something that I don't even really want to be able to phrase. I don't want to talk about strict equalities. I want to just talk about homotopies, and I shouldn't be able to, I shouldn't be even allowed to say this. Um, and also other things that behave a bit different than I'm using in practice. For example, the way that people in homotopy type theory work with products. Very often it's defined as like a dependent sum. Um, but for me, a product is just, you have X and Y, you map, mapping into the product just means mapping into the first factor and mapping into the second factor. So yeah, the starting point of our project is quite different. Like we take a step back and we look at the language that we wrote down, this model agnostic language from this joint project with Szynski, Gwen, and Walde. And the goal is, can we find a type theory that makes these, a priori informal axioms, can we actually make them rigorous in some way or another? Okay, so this is what I want to explain in this talk, at least, the very first steps of these axioms. Yeah, so for that I need to say a bit more about how this model agnostic language, how this is written down.
Bastiaan, before you go on, can I
Yeah,
clarify? So you were uh, making the point that sort of associativity of function composition, maybe thought of as like functor composition between infinity groupoids in sort of Martin-Löf type theory is too strict. Are you complaining about the sort of judgmental equality or the
yeah,
identity type?
yeah. You could say that. You could say that. So I'm not sure if I'm necessarily complaining about it, but I do notice that in my day-to-day life, I am never using judgmental equality. I would prefer to also never have to talk about it.
Mhm,
And I know I could imagine that there are ways to address this also in the usual way of doing Martin-Löf type theory.
mhm.
And I don't necessarily want to say that this is impossible. Um, yeah,
Okay.
but yeah, so this type theory I'm gonna introduce, it just basically doesn't really allow us to say equal. You just always have to provide higher
Great. So,
homo.
yeah, so your issue is not that the identity types are too strict, but rather that judgmental equality is sort of too strict.
Yeah, exactly. The identity types, they are not too strict, of course, but it's about the judgmental equalities. And also like all the computation rules. I don't want to have these strict computation rules somehow. Um, yeah, so the approach we are taking in this joint project, and I should say that yeah. So originally before I joined the project, the other authors had a slightly different perspective. They were working in the clan and tribe setting of Joyal. And then Denis Charles Szynski gave a lecture course about this. And very soon during the lecture, I was writing up the notes for this, and I noticed that once you go a little bit further into the theory, the entire language that you're using doesn't really depend on, the language of clans and tribes and this vibration and so on. And especially because the goal was to eventually, formulate this in some type theory, I decided to write up everything in in a way that doesn't refer to, like, it's agnostic about whether we're talking about quasi-categories or maybe it's going to be a type theory in the end. So currently, this is how the project is written up. There is first the basic language, and then there's a lot of theory that we're gonna that we are building up. And then, as a third step, which is sort of maybe we are now in this process of like what kind of underlying substrate can we choose? So this word substrate was something that my colleague Tashi Walda has also been talking about in his talk on HoTT roughly a year ago. Yeah, so what is this model agnostic language? It consists of two main ingredients that I want to highlight because I'm going to translate them into this type theory CaTT in a moment. So the first part of this language is just the primitive notions that we have. So we need to be able to talk about infinity one categories. We need to be able to talk about functors, natural isomorphisms, higher isos, and then we need to be able to compose functors, and we have identities and associativity. And once we have these basic notions established, we can then introduce some of the basic constructors, terminal initial infinity one categories, products and co-products, pullbacks and functor categories. And once you have these, you can start to use those to formulate more intricate category constructors like subcategories, localizations, and so on. So yeah, the goal of my talk is two parts. First, what kind of type theory describes this part one, this primitive notions? And then, I mean, this is this type theory CaTT that is in the title. And then how can we use this language, this type theory to describe these basic constructors? Right, so let's zoom in a bit more. So just to make the pattern matching a bit easier in a second, let me emphasize what this structure is really going to be. So there is like a base layer where we need to be able to talk about the objects of our theory, infinity one categories. And then there is some inductive procedure where, given two infinity one categories C and D, we need to be able to talk about functors between them. Given two functors F and G, we need to be able to talk about natural isos between them. Given two natural isos, we need to talk about three isos between those. So it's somehow, whenever you have some notion of n isos, you want to be able to say that they are equal, and equal means that you just provide an n+1 iso between them. And maybe some people in the audience might wonder, why do I say natural isos and not natural transformations? And this has to do with the fact that I want to axiomatize the infinity one category of infinity one categories and not the infinity two category. And yeah, this is a design choice that we chose because infinity one category theory is a lot easier than infinity two category theory. Okay, so and then on top of that, we need a bunch of coherences. So we need composition of functors, need composition of natural isomorphisms, unitality and associativity, but also the relation between n+1 and n-morphisms. So we need to be able to whisker a functor with a natural isomorphism and horizontal composition and so on and so forth. And this is where basically, so our project with Ivan started when Ivan made the observation that this is basically the structure of a weak omega-1 category in the sense of Grothendieck and Maltzeniotis. And yeah, I imagine that a lot of the audience is not familiar with this notion of weak omega-1 categories. So let's define what this means. So the structure, so it's a definition that comes in two parts. First, we have the notion of a globular set. A globular set has a set of objects or zero cells, x0, And then for every notion of n cells, there is a set of n+1 cells between them. So given two objects, x and y, there is a set x1, x comma y of morphisms between them. For f and g two morphisms, there is a set two cells, and so on and so forth. And then to get the notion of a weak omega-1 category, we equip this with additional operations. So these are of the form, all these things that I've been mentioning already a couple of times. Compositions, whiskerings, unitality, associativity. And the way to formulate this nicely is, this is something that Grothendieck came up with. It's the notion of a coherator. So Grothendieck originally formulated this in the setting of omega groupoids, where all the higher cells are invertible. And then Martin-Löf observed that you can generalize this to get a notion of weak omega category, where the higher morphisms are not necessarily invertible. And yeah, the precise formulation of these coherators, it's a little bit tricky maybe, and it's also not really relevant for the purpose of this talk, because it turns out there is a very elegant reformulation of this in type theoretic language. So there are these two different type theories, this GSET and CaTT, that describe these two steps. First, the language of a globular set, and then this additional language of operations that we can have in a weak omega-1 category. I mean, yeah. So I should maybe clarify that for our project, we are interested in omega-1 categories, but this type theory actually just talks about omega categories with non-invertible cells in all dimensions. Yeah, and I should also mention that this type theory was developed by Finster and Mimram, and later there were some more details about the relation between this Grothendieck Martin-Löf, this weak omega-1 category were worked out together with Thibaut Benjamin. Okay, so maybe this is a good point to jump into the actual type theory. So how do these two type theories look like? Let's start with this type theory for globular sets. So a lot of stuff looks like we're used to. So we have contexts, we have types in contexts, we have substitutions, and we have terms. And it's important to keep in mind that the types in this type theory behave very differently from the types in homotopy type theory. We should not think of the types as homotopy types. We should think of the types as encoding the n cells in some omega-1 category. So this is what I've highlighted. So the main important rule are these two rules in red. In every context, we get this type star of 0 cells. And then the rule says that whenever we have some type A that encodes n cells for some n, we have an n cell T and an n cell U, then we get a type of n+1 cells between them from T to U. And the rest of the rules, I mean, they're not so interesting. So there's an empty context, we have context extension, there's a substitution to the empty context, there's substitution extension, and then we have terms. So GSET is kind of special type theory because the only terms we can ever construct are the variables. So this type theory in itself is not very interesting, but the reason, it forms the basis of the next type theory, which is CaTT. So CaTT is going to be an extension of GSET in which we add a bunch of coherences. And before I'm just going to write down the rules, I think it's useful to motivate how these coherences should look like. So some basic examples would be, let's say we have a context in which we have objects X, Y, and Z, and we have morphisms F and G. Then in this context, we should be able to form a new morphism called the composite of G and F. Similarly, if we have a context where I have X, Y, and Z, and I have an additional morphism F prime and a 2-cell alpha, then in this context, let's assume we already know how to form composites, so I can form G composed with F, and I can also form G composed with F prime. Then I need to have a whiskering of G with alpha, which goes from G to F to G composed with F prime. And then, thirdly, I want in a context where I have all these, three composable morphisms, I can compose them in two different ways, putting the bracketing in two different ways. And I want those two one cells to be connected by a two cell in both directions, like an associator and its inverse. So how would you go about writing this down in G-sets? And this has a very beautiful answer, which I think is already due to, this notion of pasting context is, I have to admit, I don't know the precise origins, but it definitely was already present in the way that Grothendieck wrote down this notion of cooperator. And translated to this type theoretic language, it looks as follows. So basically the idea is we're going to write down which contexts do we expect to have a unique total composite. And the way we obtain these contexts are using two very simple rules. So the first is there's just a base pasting context, base pasting context, which has a singular object, just X. And then we can extend this each time we pick some dangling variable. I will illustrate it in a moment what this means. And then we add a second term y in the same type, and then we extend it with the morphism between them. So let's look at this first diagram here, for example. I can pick this object X, and then I can extend it by adding this term y in a morphism that connects X and Y. And here I have two choices for dangling variable. I can pick F or Y, but if I pick Y, then I can extend it with another one morphism to get this diagram for composable morphisms, so the context for composable morphisms. Okay, so how would you get higher cells? So let's look at the second diagram. So we have this X. As before, I extended with Y and F. And in this case, I'm allowed to say, okay, this new variable F that I have, I pick that one as the dangling variable. So if I'm gonna extend now, I have to add another term in the same type as F. So it's a morphism from X to Y, and I connect it with a two cell to F. So I get an F prime and an alpha. And now at this stage, I actually have three choices. I could now change alpha by an alpha prime and add a three cell, or I can go on extending F and I have an F double prime with another two cell. Or the thing that I'm actually going to do is I look at this Y as a dangling variable, and I'm gonna add another zero cell and then one cell. And then finally, the third context, you do it in the same way. You just add three of these extensions. So in type theoretic language, it would look like this. There is the pasting context, which is just X, which only has one dangling variable. This just X itself. And then if I have a context gamma with a dangling variable X, I can extend it with another Y in the same type and a morphism F that connects X and Y, in which F is now declared to be a dangling variable. And then we can reduce dangling variables in dimension. Whenever F is a dangling variable, I can reduce the Y, and Y becomes a dangling variable as well, and I can iterate this. So here, for example, in the second case, this alpha was a dangling variable, then I deduce from this rule that F prime is a dangling variable, and I use this rule another time to deduce that Y is a dangling variable. And then finally, if gamma is any context that has some dangling variable, we just write gamma pasting context to indicate that it's a pasting context. Okay, so this sets up this notion of pasting context. And why does this help with coherences? Well, the idea is that these contexts are precisely the ones that ought to have a unique total composite. So we're going to add a rule of the following form. Gamma is a pasting context, and we have two, let's say, n cells. So there's some type A. We have an n cell, like a term U in A and a term V in A. And these, we're going to add new constructors to our theory that are called coherences, let's say, that allow us to have a term in the type from U to V. And Of course, we shouldn't just do this for arbitrary u and v. So this rule is going to have two side conditions. There are two ways that we are allowed to form this coherence. And what it amounts to is basically expressing, first of all, we want there should be a total composite. And then second of all, we're going to express that it's unique. So the first way that we can obtain this total composite is basically, I will illustrate what these rules mean on the next slide using the examples that I had before. But what it will say is that I need to assume that the free variables in U use up all the free variables in the source part of the context gamma. So every pasting context gamma of dimension n will have an n-1 dimensional source boundary and an n-1 dimensional target boundary. And we are allowed to form coherences if the U uses up all the variables in the source. So it's sort of roughly saying U is a total composite of the source of the context. And then V must be the total composite of the target of the context. And then we get a coherence from the source to the target. And then there is a second side condition that could be satisfied, which is that, it's basically the case that U and V are both total composite of the entire context. So in other words, U and V must both be using up all the free variables in the entire context. And then we get a map from U to V, but notice that this condition is symmetric. So we actually, in this case, also get a map from V to U. And we can actually, so if we think of the case of an associator, for example, then we get higher coherences as well. So if you have an associator, then it will itself use up all the rules in the entire context, all the variables in the entire context. So any two associators will be compared to each other, and any two ways of comparing associators will be compared to each other, and so on and so forth. So together, these two rules provide the composites, the total composites in a basic context, and also provide the uniqueness for them. Okay, yeah, let's look at an example of these rules, because maybe, I didn't really define these source and target boundary of these contexts, and I'm also not sure whether a formal definition is the most useful way to explain them. So I think it's more useful to just look at some examples. So first of all, how do we form composites? I take this context with the F and the G, and so in this case, it's a one-dimensional context. The source is going to be just this variable X. The target is going to be just this variable Z. So I pick U equals Z. This is basically forced if I need to use all the variables. And I pick U equals X, V equals Z. This condition comp is satisfied. So I get a new term that I'm going to call G composed with F. What happens in this two-dimensional case? So this time the diagram is two-dimensional. So the source boundary is one-dimensional. It consists of the X, the F, the Y, the G, and the Z. The target boundary is the X, the F prime, the Y, the G, and the Z. So here I actually have several choices for U. I could, for example, just pick G composed with F, which is what I'm going to do. But I could also just take G composed with F, composed with the identity of X, for example. This also uses up all the variables. So U and V satisfy all the assumptions, and then this rule comp applies, and it gives me another coherence that I'm going to call G star alpha, the whiskering of G with alpha. So finally, what about, I've been mentioning this associator as a couple of times as an example. How does this come about? So in this case, we're going to use this rule inf. So I'm going to look at this context where I have three composable morphisms. And then if I pick U to be the composite of H, G, and F, and I pick V to be the composite of H, G, and F, but in the other bracketing, then they use up all the variables. And maybe I should clarify, when I say use up all the variables, it really means sort of semantic dependence. So, if you're using the variable F, then in particular, you're also using its source and its bound, you're also using X and Y in some sense. So This is how this notation should be read. Yeah, so in some sense, U and V are both total composites of this entire context. So the rule inv applies, and it gives a map ASOC between U and V. And the same rule would also give an inverse in the other direction. Okay. So yeah, what is the upshot? I mean, so this type theory by Finster and Mimram, it now provides a type theory whose models are weak omega-1 categories. And you might now ask, okay, why should we care about this? Because like you made some analogies with the language that you wrote up in this book project that you have, but like, can we actually use this type theory to do some synthetic category theory? Like it's maybe not so clear why we should be able to do that. And so here's the main here's a result that I proved together with Ivan. If you take any quasi-category, you can construct from it such a weak omega-1 category in the sense of Grothendieck semiotis. So somehow the two, I mean, both of these notions aim to describe infinity one categories, but they do it in a quite different way. In a quasi-category, you just you ask for lifting conditions. You say you can find certain lifts, whereas in a weak omega-1 category, you're given all the structure. It needs to be provided already. So the way to go from the left to the right is just to show that all the lifting conditions that you have provide you a way to get all the additional cells that are required by the definition of a weak omega-1 category. Yeah, I'm not gonna. So the way we actually do this is via topological categories, and if there are people interested in this, I can talk more about this at the end. But it's sort of slightly tangential to the topic of the talk, so I won't go much more into this.
Excuse me. So, what's the difference between a weak omega-1 category and just a regular omega-1 category?
I don't know what regular omega-1 category is, but the important thing is that composition is not like there's no strictness whatsoever. So you're never allowed to say, for example, H composed with G composed with F is equal to H composed with G composed with F with the other bracketing. Like, or composing with the identity is equal to just F itself. All those rules that you like, all the time you would like to write an equality, what you're gonna do instead is just writing down a map, and then you also have a map in the other direction, and then co-inductively you require, yeah, I mean, you have a lot of coherences somehow. And it's the weakest possible notion of omega-1 category. If that's what regular means for you, then
possible to write down in the type theory that whole co-inductive stack of things? Or like in this type theory, internally, is it possible to write down what equals is?
if you mean if it's possible to internally write the entire stack of invertibility data, so it's interesting that you asked this because there was actually an article that came out today on the archive, which is precisely about this question. Can we like this is by, I hope I say the names correctly, Benjamin Champion and Markakis. I hope I don't butcher the pronunciation. They precisely address this question basically. So they extend the type theory cut with an additional type constructor inv, which allow you to talk about invertible cells. But yeah, I'm not sure if I would really call this like equality. Yeah, I mean you can call it equality, but you have to be a bit careful because a lot of people in the like working on these omega categories, they have a stronger notion of equality in mind when you say that. Yeah, but the upshot of this is that we can in particular now look at the quasi-category cut infinity one of small infinity one categories. It is now defined such an omega-1 category, so it's amenable to this type theory cut. We can probe it, we can use the language of cut to now look inside this quasi-category. And now the question becomes, can we take these axioms that we have written down in this joint project, and can we formulate them in this language? Can we access them in this way? So this is what I'm gonna talk about next. Okay, so what kind of constructors do I have in mind? Well, we want things like a terminal object in our omega-1 category. We want to talk about products and about pullbacks, and maybe some more general notions, but let's start with these. So remember that an object ought to be terminal if for every other object y, there is a unique map from y to x. And then similarly, a product of x and y is some object that comes with projection maps to x and y. And the rule says that for every map into x, like for every object z, and for every map f from z to x, and for every g from z to y, there is a unique map f comma g from z into the product, whose first component is f and second component is y. And of course, I mean, this is, the way I'm writing it here is sort of the way you're used to it. But we have to be a bit careful what we mean by unique in this case. If we want to translate this to the type theory CaTT, unique cannot mean the usual strict notion of uniqueness where any two elements are like strictly equal. So instead, we're gonna do it, the way that we have also been dealing with the coherences. So uniqueness, we're gonna say that a certain type A that encodes a certain type of n cells has a unique term if, first of all, there exists such a term, and second of all, for every x and y in A, there is a unique term between x and y. So this is like a co-inductive definition in some sense, and in particular, if I swap the roles of x and y, I get a unique cell in the other way, in the other direction, and then the uniqueness co-inductively allows us to get also the higher coherences somehow. So I guess this is quite, I mean, people from homotopy type theory will probably be used to such a description where, if I take a homotopy type, it's called contractible if, first of all, it's inhabited. I have some x, and then for every two x and y, the path type, the identity type between them is itself contractible. This is sort of the analog. And if I would have to explain this to a topologist, I would say, like, let's think of the A as a topological space. Then we have first of all, it's non-empty, so it has a point. And then for every point, I can extend it to a path between them. And then for every two paths that have equal endpoints, so it's like a map from a circle, I can extend it to a disk. And if you go on and so forth, like, it basically amounts to saying that every map from an n-dimensional sphere into the topological space can be extended to a disk. So this is just the usual notion of weak contractibility of a topological space. Okay, so let's now look at this first rule for terminal objects. And we need to make precise that, all these iterated Hom types need to be inhabited. That's basically what now our notion of uniqueness amounts to. So let's first make precise what this notion of iterated Hom type means. So this is what we wrote down, and let's introduce a judgment for this. So we're gonna say that B is an iterated Hom type of A if it is constructed in one of the following two ways. First of all, A is an iterated Hom type of itself. We just have done 0 iterations of forming Homs. And then second of all, if B is an iterated Hom type of A, and I have terms T and U of B, then the Hom type of B is itself an iterated Hom type of A as well. And now I can state the rule for terminal objects very cleanly. It is just as follows. First of all, there exists an object called, let's call it 1. And then second of all, whenever I have a type B, which is an iterated Hom type of this type of morphisms from X to 1, then I ask that it's inhabited using some term constructor. Let's call it exclamation mark or shriek B. So yeah, so for example, for any object, I can apply this now to the type B, which is itself the morphism type from X into 1, which gives me a map from X to 1. If I have two maps, F and G, that go from X to 1, then I can apply this rule to the type of morphisms from F to G, which is an iterated Hom type of this. So I get a map I get a 2-cell from F to G, but I can swap the roles of F and G to get a 2-cell from G to F as well. And then, now I get all the higher coherences that you would ever imagine you would want to have, you get them also as well. So for example, if you compose the streak FG with the streak GF, you get something that goes from F to F, which lives in an iterated Hom type of X to 1. The identity of F also does, so there must be equal. I mean, there must be a comparison map in both ways, and so on and so forth. So this automatically sort of makes sure that all these comparison maps we have are in particular invertible. Okay, so this idea, it's fairly easy for the terminal object because there's no additional data that we need to provide. What happens for the case of products? So, I mean, we want to have a term of the Hom type. I mean, yeah, so a term of the type from Z into the product should be given by specifying both of its components. So if we didn't iterate at all, it's clear how we would formulate this. We would just say, okay, we have a term F from Z to X. We have a term G from Z to Y. This should give a term F, G from Z into the product. Let's look at the next case. So let's say that we have two maps into the product, H and K. In this case, the way we should be able to produce a map between, like a 2-cell between H and K, would be to say, let's assume we know that they are, we have a 2-cell after composing with the first projection map, let's call it alpha. And let's also assume we have a way of comparing H and K after composing with the second projection map, let's call it beta. Then we should be able to combine those two into a 2-cell alpha, beta from H to K. And now, I would like to say, okay, etc. And I mean, I am gonna say etc. But it might not be immediately clear how you generalize this. So what we need is a notion of higher whiskering. So let me briefly tell you about what this means. So yeah, so if I have a morphism G from Y to Z, I already explained to you how I can form composites with this. So if I have a morphism F from X to Y, we have this context that encodes composable one morphisms. And I realized that I should have clarified actually. In the rule where I wrote down the coherences, a subtlety that I ignored was we don't just want to have those coherences in the actual pasting context where they're constructed. The actual rule, I didn't write it for simplicity, but the actual rule allows us to transport it using any substitution into any other context. So even if you're not in a pasting context, whenever you have two composable 1-cells, you're able to substitute in, there's a substitution to the context which has only those two 1-cells. There we can find the coherence, and then it's going to be transported into our context. I mean, this is maybe just a technical side remark, just if people were confused about this. Yeah. Okay, so I got this notion of composite. I also explained to you how to get this notion of whiskering, and we can inductively repeat this process. So whenever I have now a 3-cell between alpha and alpha prime, I need to be able to whisker this 3-cell with G to get a 3-cell from G star alpha to G star alpha prime, and so on and so forth. And if you do this, inductively and in some way, you will end up with a construction that takes some type whose iterated Hom type. I mean, it's an iterated Hom type of X to Y. And then for any alpha inside A, we get some notion of higher whiskering. Okay, so because of space, I have to remove this explanation of higher whiskering again. And now I can formulate the rule for products. So first we have the formation rule. It says for objects X and Y, there is a product, X times Y. And then the universality says whenever I have some type A, which is an iterated Hom type of the type of morphisms from Z into the product, and I'm given a term of A after whiskering with the projection to the first factor, F, And I have also a term G after, like in A, after whiskering with the second projection. Then I obtain this pair F comma G inside A. And then we also need coherences that ensure that the first component of F comma G is F, and the second component of F comma G is G. And these rules that I mean, the base two cases of this rule are written out at the top. So if you take A to be equal to maps from Z into X times Y, then this whiskering procedure is somewhat trivial in nature. This first projection star A will just become the type of maps from Z to X. The second one will just become the type of maps from Z to Y. And then we see that it's precisely this first bullet point. And similarly in the second case. So given X and K, I can take A to be equal to the home type from H to K. And yeah, then it precisely amounts to the second bullet point. So the rules for pullbacks are similar in nature, but they are more intricate because I need to be talking about whiskering of cones. So you have now two morphisms from X to Z and from Y to Z. And I have a commutative square, and I need to be talking about whiskering of such a commutative square with another morphism. And it took us a while to figure out how to phrase this, and eventually we managed, but even then it was tricky to prove comparisons between different universal constructions, for example, associativity of pullbacks. So what we ended up doing is constructing whiskering for a general notion of cone types, which, yeah, it's a bit technical, and I will not go into detail into it right now. But it's basically a way to take this idea of what I've been describing, how to formulate the universal property for the terminal object and for products, and write it down for an arbitrary sort of diagram. You know, if you have if you have some kind of diagram shape, you can write down the universal cone for that diagram shape. And one very important ingredient that we make use of is a certain naturality construction in CaTT, which allows us to make precise this notion of iterated home type, not just for an individual type, but even for these cone types. So this naturality construction was constructed roughly a year ago by these 5 authors: Benjamin, Markakis, Offord, Sarti, and Vickery. Yeah, and as mentioned, I will omit the details on this. Okay, and then there is one last construction I want to explain how to do in CaTT, which is the internal hum. So we have objects X and Y, and then the internal hum should be this bracket X comma Y. It comes equipped with an evaluation map from the internal hum times X into Y. And if I have such an evaluation map, I can form the uncurrying of any map into the hum type, which is defined as it's a map from Z times X to Y, which is given by first taking F and taking the product with the identity. So the universal property of products allow me to construct this in more detail. I'm mapping into a product, so I need to specify what the first component is and what the second component is. The first component is obtained by starting in Z times X, first projecting to Z, then applying F. The second component we map into X, so we can just take Z times X and just project it to X. And I mean, you can define products of arbitrary maps in this way. And then I compose with the evaluation map. And the universal property of this internal hum should be that we can reverse this process. So for any map Z times X to Y, there needs to be like a unique currying of this map whose uncurrying is G. So, I mean, yeah, the way that you would phrase this is similar to the previous rules. So we have for every X and Y, the internal hum from X to Y, we have an evaluation map. And then for any type, which is an iterated Hom type of maps from Z into the internal Hom. And for any G, for any like uncurried map, so this is a bit tricky to phrase because you would need to, generalize this thing that I did for whiskering. You would now have to do this, for taking products of a type with this X. But yeah, let's ignore the details on this for now. And then I have to whisker with the evaluation map. Then the rule says there is an uncurried term inside A, together with a coherence that relates the original G with, I take this is basically the uncurrying of this curried GC. So you take the product with X and then whisker with the evaluation map. Okay, so this is,
Sorry,
yes.
when you write EV star, does that star, should I think of it as taking this judgment as an argument, the iterated Hom? Like the star depends on how many times you've iterated the Hom, right?
Yeah. Oh, I'm noticing that it's actually unfortunate notation that I'm using star in two totally unrelated ways. I didn't notice before. Anyway, yeah, that is right. So the star, you could choose to decorate it with a subscript that sort of remembers the dimension. So this cell over here can have an arbitrary dimension, like it can be an n cell. And in this case, it means like whisker the n cell with this one cell to obtain a new n cell. So it somehow, yeah. But they all behave kind of similarly, like you would define them inductively in some way. Okay, so let me wrap up. So the upshot is what I've described so far is a type theory that describes, like, the models of this type theory are infinity one categories, which have products, pullbacks, and internal Homs. And I'm talking about infinity one categories mostly because this is the use case that we have for it. But if you look at the rules, there isn't really much intrinsic reason why I have to restrict myself to infinity one categories. I mean, because the type theory itself actually describes infinity categories. So maybe some people in the audience are interested in having products and pullbacks and so on in infinity categories. And in the future, we hope to do more of the axioms from synthetic category theory internal to this type theory cut. So what would be things that we will be doing? So far, these objects of this underlying infinity one category we're describing don't have any internal structure. But in the end, we would like them to behave like categories themselves. So we need to be able to talk about morphisms inside these things and commutative triangles and so on. And the way we would go about doing this, so I should maybe make clear that the things I'm describing now are things that I haven't done yet in the project with Ivan. Those are just things that are in the book project together with Sisinski and Gwen and Walde. So we would introduce the walking morphism and the walking commutative triangle, and then maps out of those into another synthetic category would encode morphisms and commutative triangles. Then you can phrase things like the seagull and the rest conditions that enforce these synthetic categories to actually behave like categories. A next step would be to formulate the notion of a groupoid and then the groupoid core. And this again would be formulated in the language of CaTT. It would say that if you have a map into a category from a groupoid, you get a unique map that maps into the groupoid core. So here I'm using capital letters X and Y, X and C. They take the same rule as the little x and the little y that I had before, except that now I want to think of these as, categories by themselves. And once we have this, we are basically like all the higher categorical constructions probably won't really need to talk about this language of CaTT anymore. If you look at the way that they're written down in our book project, they are already formulated in some kind of higher level language where we can define the mapping groupoid between synthetic categories C and D. defined as the groupoid core of the functor category C, D. Okay, so yeah, so this is all quite speculative, I have to admit, because a lot of this progress in the project with Ivan it was quite recent, so we will see how things develop. But I think that this approach of using this type theory cut is actually it might be quite interesting for other purposes as well, even if you're not interested in synthetic category theory. So I would be excited to see other people work more on this. I don't understand why this type theory has received so little attention. It just seems so beautiful to me. Like, for example, the fact that you can directly interpret any infinity topos directly, you can directly probe it using this new type theory cut. Instead of, in HoTT, you would have to sort of rigidify it first to make it into a model category and prove it has the correct properties, and then you can interpret HoTT somehow. Yeah, so um, I'm looking forward to see if my talk inspires some people to look more into CAD as well. And on this note, I think I will end my talk here. Yeah, there are some references that I will just show briefly in case at least they show up in the recording. Okay, thank you for your attention.
Great, thank you very much. So we will do either our visual applause or using the reaction button. And I'll open the floor to questions. So if you have a question, feel free to unmute your mic and speak up. Okay, I will start with the question. You gave examples of how to define terminal objects, products, HOM types. Maybe you can flip to the HOM type slide. I think it was 16.
This one?
Yeah. So so the idea you give at the beginning is that, for every G, there should be a unique G sub C with a certain property. But the way you formulate that is a bit more complicated. You have to form these iterated, I forget what you called it, the delta star construction. You had already defined what unique means, but you don't have a way to use that definition here. And it feels to me what you're unable to do is form the type of G sub C's that satisfy a condition. The condition G sub C to the U is isomorphic to G. If you could internally make that type, then you could just say it has a unique inhabitant and be done. So
no, I mean, are you complaining that is your question specifically about the rule for internal HOMs, or would it also apply to the rule for pullbacks and products?
It also applies to those, yeah. So in all cases, instead of just saying that a certain type has a unique element, you had to list a bunch of inductive rules, and you couldn't just rely on this one definition of uniqueness.
Well, in my mind, I'm just making precise this one definition of uniqueness. This one definition of uniqueness, what does it say? It says that I take this type, Z, it maps from Z into the product, and I see what you're saying. Yeah, I see what you're saying. Like, it's not uniqueness of a type, it's so
I guess what I'm saying is if you had a type former that let you say the type of morphisms that satisfy a condition, or really the type of morphisms along with an isomorphism, it's like a sigma type. If you could form that type then all of these definitions would just be form a certain type and say that that type has a unique element.
Yeah,
But your language doesn't seem to let you form sigma types like that.
that's correct. That's correct.
So
Yeah.
that one tool could solve all these problems. And I don't know if that's an option that could be added. I'm not sure if it makes semantic sense.
So I think the way we are thinking about it is to do something similar, but instead of adding it as an additional rule to the type theory, we're gonna formulate this in a a meta theoretic sense where yeah, I don't know, maybe this is not you wouldn't consider this a satisfying solution, but we would we would bundle all these things into something that you might call these cone types that I mentioned, like it's here on this slide. Um, and um, yeah, so we would not be internalizing this dependent sum as a constructor in a type theory, and somehow this is a little bit by design. Um, the type theory is very simple. Like like you cannot do much with your types. If you start adding things like dependent sums, I would imagine that you move more and more like just to the usual HoTT. Like you would also need to introduce computation rules and so on for dependent sums. And I mean, maybe, yeah, I would be interested in having, maybe there is a way that you can do this, but so far we haven't been considering doing this.
Okay, thank you.
I had a follow-up to that. Um, so you mentioned that equality can kind of be defined in a meta-theoretic way, um, where you say that you have, like a coherences tower or something, like for all n, you have this collection of coherences. Could you use that in order to like basically to sort, I mean, it's not exactly internalizing it, but like if you had that as a sort of explicit bit of syntax that you could use to refer to like equality, like an equality, I mean, not exactly an equality type, but then it gives you something on which to say that that type is unique in order, like basically define a stack of meta-theoretic operators over top of this type theory that allows you to talk about more complicated forms of uniqueness that might unbundle to like this definition that you showed for pairing, for instance. Does that make any sense?
Um, yeah, um,
I mean,
yeah,
like
I'm not
building
sure.
higher order sort of objects that talk about like, two things are equal if you can build this thing, and then this type is unique if, all of its higher things have, some coherence to, like you can write down in the meta theory a bunch of properties that express these words that you're using, like unique and so on.
Yeah,
And then allows you to sort of bundle these up in a way that sort of might generalize a little bit better where like it makes it more obvious how to say, oh, what is a unique, what does it mean to have a pullback? Because now you have like a language that you're building up of like what is equality so that you can just sort of deploy that rather than having to reinvent equality every time you're writing down a new notion. Does that make sense?
yeah, this makes a lot of sense. Um, so yeah, um, I should maybe something that I should also emphasize is that um, the the way we intend to use this is more like a meta language. Once you can probe, like this is a meta language to probe inside the category, the omega one category of like the infinity one category of infinity one categories, and inside there is going to be an intrinsic notion of contractibility. Like there is going to be an intrinsic notion um of an infinity one category, you know, to be contractible. It means equivalent to the point, and very soon a lot of things are not going to be phrased at this meta level language. It's going to be phrased internally to the infinity one category of infinity one categories. So a lot of these considerations about, making all this meta language more elegant and capturing this notion of uniqueness, somehow it's not precisely our focus. Like I'm pretty sure you could probably do that. You could probably um, add some operators that make precise this notion of uniqueness. But I don't feel like I mean, this is not really the direction I would like to go into.
I mean,
I'm gonna
certainly
use,
things get a lot easier if you have an internal object that is actually an equality type, right? Or something that is isomorphic to this meta equality type. Then that saves you the trouble, right? Yeah, then you never have to worry about the meta stuff, and you'd much prefer to use the internal equality if you can, and that's like what you get in HoTT.
yeah, I mean, but internal equality will just mean, I mean, at some point you have these synthetic categories and they will have, they have home group, like they have home groupoids, and you can talk about invertible maps and those, like it's all going to be formulated internally, not inside CAT somehow.
I mean,
Um,
is there a reason you can't just introduce, in addition to having this arrow, and like so far you've sort of tried to avoid having equality directly in the language, but couldn't you just have an equality and then have in the same, you have your pacing context and says, equality has all of this higher structure and it's all coherent and so on.
um, yeah. So as I mentioned in this article, yeah, I'm not sure if I totally got the question, but like, you can directly say when morphisms should be invertible,
Mhm.
and getting all
Uniquely
the,
invertible. Can you say that it like all of these are defined as sort of an infinite conjunction kind of a bunch of judgments, which makes it kind of
yeah.
awkward to work with. Is there a way of writing it down as a single judgment?
Um, no, I don't know. I don't think so.
Mhm. But I mean, if you were to add
I
like
don't,
an equality type or several other kinds of things, those would be ways of just essentially by fiat saying, yes, there is a internal judgment that I'm adding to the system that's going to allow me to say equality. And then and then you can use that whenever you need one of these uniqueness or whatever.
um, yeah, I mean, I feel like we might be talking past each other a little bit. I mean, there is this article that just describes a type, and it's called inv of a term, and then getting a term of that, um, just describes that it's invertible, and it will sort of co-inductively generate all the higher coherences you might ever
Yeah,
need.
yeah, yeah.
If
That
that's,
would do the trick.
yeah, that you can certainly do. I mean, I say certainly, but I didn't know about it before this morning, actually. Um, uh, so this is something you can apparently do, yeah. So
Mhm.
I'm recommending just to look at this article that they wrote.
Okay, there's a question from Gothenburg.
Okay, hello, can you hear us?
Yes, I
Okay,
can.
so we missed a definition, I think. So at some point, this arrow with a squiggle on top of it started appearing, but we weren't sure what that was. Yes, there.
Oh, oh, right. Yeah, I should have spent more words on this. So, this could mean two things. The way I'm personally currently thinking about it is as follows. It just means an arrow, except that um so there is this type theory cut that I've been describing. There is also a variant where you assume that every cell of dimension 2 or higher is invertible.
Hmm.
And this would just be you add a third way of getting coherences. So you just say for any u and v of dimension at least 1, you get a sorry, but how should I formulate it? Um, yeah, I forgot the precise way of formulating it right now. Sorry about that. But it would enforce that um, all the higher cells are automatically invertible. So this is something that this version of CAT was something that Ivan Kobe wrote out in his master thesis. So this is the way that I'm currently thinking about it. A second interpretation would be, okay, let's not assume that all the higher cells are invertible. Let's just work with the usual CAT, as I've been describing it in my talk. And then this could be interpreted as adding a term of this you first of all have a map from F to projection 1 star F comma G, and then you also have a witness of this invertibility type as developed in this article that was posted on the archive this morning. So this is now a second way that you could interpret this.
Okay, I think that answers our other question, which is whether you are truncating things or not.
Yeah, we're never truncating anything.
By truncating, I mean inverting above a certain dimension. Like
Oh, sorry. Oh, yeah, we're
values.
definitely doing that.
Okay.
I don't know.
Yeah.
I don't know if it's necessary. I think a lot of things we are doing in our project don't need that, but
Mhm.
we are only interested in describing the internal language of an infinity one category. So in my mind, this is the only thing I'm thinking of basically. Yeah.
But so you think that in theory you could be talking about the infinity two category, but for simplicity you prefer to stop at one, is that right?
That's correct. That's correct. Yeah.
Okay. I think that's every question we had.
Yeah.
Okay, thanks.
Yeah. I mean, the reason is that to get the higher structure, for example, natural transformations, they can be phrased as morphisms in the functor category. Like once you're already at infinity one, you can get the higher structure for like, I mean, yeah, you get it for free in some sense. Like it becomes accessible to your language. So the natural transformations are not encoded by thinking of CaTT as an infinity two category. They are just encoded because we can talk about morphisms in our functor category. That's basically the upshot.
Okay. Thank you.
Are there more questions? Okay, if that's it, then let's thank the speaker again. And that's it for today. We will be back in 2 weeks.